Have you ever wondered how engineers make sure a control system responds smoothly instead of going unstable? In this video, we will understand stability analysis in control systems, what it means, why it matters, and how engineers determine if a system is stable or not. Let's get started. In control system, stability means the system's output should return to a steady state after any disturbances. If it diverges or oscillates without settling, the system is unstable. Mathematically, stability depends on the poles of the closed loop transfer function. In any control system, the closed loop transfer function relates the output to the input when feedback is applied. It's usually written as T of S is equal to G of S divided by 1 plus G of S H of S, where G of S is forward path and H of S is feedback path. Here we are utilizing the negative feedback, so 1 plus G of S H of S. Poles are the values of S that make the denominator of T of S is equal to 0. Or in other words, they are the roots of the characteristic equation. Here the characteristic equation 1 plus G of S H of S that's equal to 0. The number and location of poles tell us whether the system will oscillate, settle, or diverge. The key rule: if all poles are in the left half of the S plane, the system is stable. Let's consider the system. The x-axis represents the real axis and y-axis represents the imaginary axis. When the poles are located in the left half of the S plane, the system is said to be stable. If any poles lying in right half of the S plane, the system is unstable. If poles lies exactly on the imaginary axis, the system is said to be marginally or limitedly stable. Poles can be real or complex. In case of real poles, it represents the exponential responses that decay or grow. Sometimes complex conjugate poles behaves the oscillatory system response. Let's take an example. Suppose we have G of S, H of S, yes, that's equal to 10 by S into S plus 2. As we mentioned, the T of S is equal to G of S whole divided by G of S, H of S plus 1. Once you are substituting the values for G of S into H of S, we are getting the T of S is equal to 10 by S square plus 2S plus 10. Setting the denominator is to 0 gives the characteristics equation S square plus 2S plus 10 is equal to 0, will yields S equal to plus minus 1 plus or minus J3. It has two poles, both have negative real parts, so the system is stable but oscillator. The further left the poles are, the faster the system settles. Consider here, when the poles are further left, the system faster the settle. Poles closer to the imaginary axis cause slower or oscillatory responses. So, adding feedback changes the denominator and hence the shift the folds. That's why feedback can make an unstable open loop system stable or vice versa, depending on gains and polarity. So, whenever you design or analyze a control system, the first thing to check is whether the pole are. In real life, this principle governs everything from motor drives to autopilot systems. Engineers always look at the closed loop poles before finalizing the control gains because stable poles mean a safe, predictable system. In control system, we can analyze performance in two ways. The time domain shows how a system's output changes over time, like how quickly a motor reaches its target speed. The frequency domain shows how the same system reacts when we vary the input frequency, just like testing how speaker performs across low and high tones. Both perspectives are essential. Let's start with the time domain. Here we apply the test signals like step, ramp, or impulse and see how the output evolves over time. Most often we use the step response because it clearly shows the system's behavior from rest to steady state. From the step response, we can measure key performance indicators like rise time, peak time, maximum overshoot, settling time, and steady state errors. So, the rise time how indicates how quickly output increases. The peak time is nothing but when it first reaches the maximum overshoot. 50% of the target yields the delay time. When it settles the desired value, we can derive or we can predict the settling time. So how long until it stays steady will represent the settling time. And the steady state error, the small gap that remains between desired and actual output. Consider a standard second order system with this transfer function. Here, omega n is the natural frequency and zeta is the damping ratio. If zeta is small, you get oscillations underdamped. When zeta equals to 1, it's critically damped. You can get fast and smooth response. If zeta is greater than 1, it's over damped. You can get slow but stable response. Now that we understand how systems behave in time, let's see what happens when we look at them through frequency domain. In the frequency domain, we apply sine inputs at various frequency. And observe how the system's output changes in amplitude and phase. This approach helps engineers assess stability, resonance, and bandwidth. In real world systems, both analyses are vital. For example, in autonomous drone, the time domain tells how fast it stabilizes after a wind gust. The frequency domain ensures it does not vibrate at certain frequencies. Engineers combine both views to build robust, precise systems. Now, stability is not just black or white. We have absolute stability and relative stability. Let's see what this means. Absolute stability is a basic yes or no check. It tells us whether the system is stable at all. Stable. The output eventually settles to steady state value. Unstable. The output grows without bound or oscillates indefinitely. Consider two systems that both eventually settle. One may oscillate a lot and take much longer to reach steady state. Even though both are absolutely stable, their performance differs. This is where relative stability comes in. Consider system G1 has poles. Consider system G2 has pole P2 far away from the imaginary axis. Relative stability indicates how stable a system is, describing how fast and smoothly it settles. In a closed loop system, the poles of the transfer function determine the system's behavior. Poles with negative real parts contribute to the stable response. Poles with positive real parts contribute to instability. Some poles dominate the system's time response, while others have little effect. These are called dominant and insignificant poles. Dominant poles are the poles that most significantly affect the system's transient response, that are usually closest to the imaginary axis. Yeah, small, consider the small real part. For example, G1 system has the pole 1, it will be near to the imaginary axis, that means it has small real part. For example, the same system has P1A, P1P. The P1A considered as the dominant pole because they determine settling time, rise time, peak or shoot. Even if other poles exist further left in the S-plane, their effects decays quickly and is negligible. So insignificant poles are poles with large negative real parts. Comparatively, the P1A is dominant pole where P1C is insignificant. They decay much faster than dominant poles. Their contribution to the overall response is small and often ignored in approximate analysis. This simplification helps us analyze relative stability without complex calculations. The relative stability can be inferred by looking at the location of dominant poles, which are closer to the imaginary axis, so the slower decay and less stable, smaller damping, longer setting time. Farther from the imaginary axis, it has faster decay, more stable, where larger damping and quicker settling. So, even if the system is absolutely stable, the dominant poles tell us how stable it really is. So here, the G1s have the dominant pole P1A, where the G2 system has the dominant pole P2A. But comparatively, the G1 is less stable than the G2, where the G2 poles are far away from the imaginary axis. So it tells us how the stable it really is. That's all for relative stability. In the next video, we will dive into time domain and frequency domain methods for analyzing the system stability.